Well, good afternoon, everyone. Welcome to our presentation. My name is Jens Hughes. I'm a vice president with Jensen Hughes. And today we are talking about a great presentation on safety solutions for lithium-ion testing facilities. So we want to talk to you about testing labs and what is important to be aware of in terms of hazards and what to do to protect your processes and so on. I have with me today our battery safety expert, Dr. Jihan El Ouaragli, as well as Mark Susky, our technical fellow at Jensen Hughes. This is the agenda we have developed for you guys. So I'll give a very brief company overview. I promise to keep it to a minute or two. And then we'll dive into the review of the battery hazards. I'll turn it over to Jihan at this point. We'll talk about performance and certification testing, typical lab configurations, the importance of these tests, and what that means in terms of safety. We take that safety bridge and talk about, hey, what hazards are they? How are we identifying them? How do we make sure that we capture them? Then we can evaluate them properly, and then build that all into a risk assessment to make sure we have proper protection in place. Lastly, we will review then some like computer modeling techniques, and we will highlight 2 or 3 case studies where like some real deflagrations or explosions have happened at testing labs to underline the importance that this is real and we need to address it. And then to give you guys some value in your time here, we have summarized the key takeaways in 3 simple bullet points summarizing what we discussed today. We're going to try to coast through this in about 35 minutes, so we have 10 minutes for questions and answers at the end. If you like copies of the slides, there are QR codes on the chairs. If you scan those and if you contact me there, I'd be happy to send you those slides, okay? So Jensen Hughes, who are we? We're a global engineering firm. We primarily work in safety, security, and risk-based engineering. So it's our job to make sure people are safe and that the operations profile of a company has low risk. We have about 17 employees, 90 offices worldwide. We have a very strong presence in North America, but as you can see, we are present on several other continents as well. We have developed on about 40,000 global projects, and we are literally on hundreds of technical codes and standards that we help develop. When it comes to battery testing, manufacturing, electric vehicles, and energy storage systems, here you can see what areas of expertise we typically work in, such as storage of batteries, battery testing, hazard mitigation analysis, emergency response planning. We're going to talk about that more than once today and how important that is with laboratory facilities, making sure that you meet the letter of the code and follow codes and standards, and so on. All right, without further ado, I'll hand it over to Dr. Jihan to talk us to the technical aspects.
Thank you so much, Jens. Good afternoon, everyone. So I think now you all have an idea of what we can do, our capability, and what we can help you with. So let's dive into understanding one of the critical aspects of performing safe battery testing, which is understanding the hazards of lithium-ion batteries. I think you are all familiar that lithium-ion batteries start at the cell component. So the cell is the smallest electrochemical component of a battery. And basically, it has the component that you see on the image here. You have the electrodes, the cathode and the anode, then you have the plastic separator in between, and then you have the electrolytes. And basically, you can see during charging the process of how the electron moves between the anode and the cathode and how the lithium ions get deposited on each of the electrode during either charging or discharging. And lithium-ion battery cells come into different types of geometries as well as different chemistries. And you can see here we have three types of geometries. The most common, the cylindrical, the prismatic type, and the smallest or the thinnest type, which is the pouch type. And when it comes to chemistries, the cathode is what define the cell chemistry. So the coating on the cathode define if you have an NMC type, an LFP type chemistry, as well as other chemistries such as NCA. And how do we actually use the cells? So the cells are either packed into a module or a pack to achieve that specific energy density that the application require. So they are usually packed into parallel or series to achieve the specific energy density, increase the voltage or the current based on the application. So what is the most significant hazard of lithium-ion batteries is thermal runaway. So I think you all heard about thermal runaway, how it's an electrochemical, and it's a chain of reaction that releases excessive heat. It's uncontrollable. Once a cell goes into thermal runaway, it cannot be stopped. So usually during charging and discharging, there is some amount of heat that is being generated, but it is always dissipated properly. But in case if the cell is not able to dissipate that excessive heat, then you have an uncontrollable type of heat that is being generated. And that's what we call thermal runaway. So once thermal runaway starts, it cannot be stopped. And the initiating events for thermal runaway varies. It may be electrical events, so such as overcharging, over-discharging, short circuit, as well as you may have mechanical damage that could cause the battery to go into thermal runaway, if it's a puncture, crushing, or vibration. There are environmental conditions. So if the batteries are in excessive heat or excessive cold, so outside of the manufacturer operating condition, then they might go into thermal runaway as well. And we also talk about design manufacturing defects. So if there are loose parts or basically there are impurities in the battery manufacturing, then that might also cause thermal runaway in the future. And as well as aging, so successive cycling of discharge and charging of the cell might also cause thermal runaway. So what would happen if a cell went into thermal runaway? If you have a module with 10,000 cells and one cell went into thermal runaway, then you have propagation risk. And the factor for propagations are usually the heat transfer, so from the cell to the adjacent cells, as well as the design geometry. So if you don't have passive barriers that separating cells or separating modules, then you may have actually a risk of propagation if one cell went into thermal runaway. There is also electrical interconnection. So we're talking how the cells are usually packed into series and parallel. So think if there is a short circuit in one cell, there may be a type of electrical faults that will propagate into the adjacent cell. And we're talking about battery management. So battery management is a very important aspect. The BMS, if you heard about that, that's a battery management system. It's what actually monitors the cell operating condition, monitor the voltage. If it detects a fault in a specific cell, it's what is able to disconnect that cell to avoid that we will have a more escalating thermal runaway event to the adjacent cell. So as you say, the initiating event may vary, the factor for propagation may vary, but the consequences are usually pretty the same. So we summarize here all the possible consequences. So once a lithium-ion battery cell went to thermal runaway, usually have flammable gas generation, and if that gas is ignited, so you will have fire risk. If you don't have an ignition source, then you might have an accumulation of gases and the risk of explosions. And these gases contain hydrogen, so CO2, and there is also a risk of toxicity, so HF gases. So these are basically the common consequences. And we have here some videos here. These are actually from our testing lab in Baltimore. So these are various types of cells, various geometries, various chemistries. And you can see one of them, like the right-hand side, is basically a nail puncture test. The other one is like heating with a torch. And you can see how the events are pretty the same. So that's why we highlight why it's important when doing this test to understand if you're specifically doing abuse test, even if you're not doing abuse test, but doing electrical component testing, you're testing the electrical cycling, doing cycling test. It's good to understand that these are the types of hazards or the consequences. So fire safety, explosion control, ventilation, having an emergency response plan in place are all important on how we would deal with these type of hazards in a battery lab, testing lab. Actually, it might go to any types of applications of lithium-ion batteries. And yeah, so how do we actually deal with this hazard and make sure we have good batteries that can be implemented into actual products? Then we talk about performance certification and testing. So we try to differentiate here the performance certification, the certification and test standards that are specific for e-mobility and electric vehicle. And then we have another slide that summarizes energy storage systems. So you can see that the typical tests performed are covering the mechanical aspects, you see vibration and shock testing, there is overcharge testing looking at the electrical resilience of the batteries. There is also full-scale fire testing, which actually it's a great tool to get an idea of what could be the fire size, what could be the most excessive hazard in when we have actual or worst-case scenarios. And at the same time, we also have this summary table for lithium-ion battery ESS system. So you can see that usually certification and test standards cover the cell, the modules, the pack, the rack, the unit, as well as the entire system. So the UL 9548 is one test standard that are actually looking at thermal runaway specifically in battery energy storage systems. And there is a summary of the typical tests performed, so it's pretty similar tests. You might also see seismical, structural type of testing as well, environmental testing, temperature cycling, and also large-scale fire tests. So having burned the whole thing and see what's actually the peak heat release rate, what's the fire size, what could we recommend in terms of separation. So there are all of these testing that actually give a lot of good inputs for us. And yes, so here is a summary why testing is important and why actually we, in testing lab, we try to get data, we try to test the batteries. So first of all is performance and reliability. So we want to confirm that actually the batteries that we manufacture in the lab are able to behave in the field when we have actual condition like temperatures, all of this type of exterior effects that could influence the behavior. And we can, so with testing, we can also identify the potential failure points and any defects that may be in the system that we should be thinking about. So quality control is important. Testing is actually one of the first piece to get those systems listed, certified, be able to go to the field and ensuring compliance with industry standards. So all of the industry standards require tested and listed components and systems. And last piece, which is also important, so why full-scale fire testing has a great, because we get actually good critical inputs from that for us as consultants and engineers to help design those mitigation measures in place in terms of fire suppressions, detection systems, separations, and most importantly, emergency response plan of what is the extent of the hazards and what we could do better to help protect the people, protect the facility as well. And we have here a general safety strategy. So this is good to remember. It applies to battery testing lab. It may apply to energy storage systems, any types of facilities. So there are like 4 components, big components. So first of all, we have monitoring and preventing. So that starts as, for example, the battery management system, the sensors that we have in the batteries. Those are the closest one to the cell. So those are able to kind of detect any initial signs of failure, and the BMS, for instance, is able to disconnect the cell in failure. We also have the second piece, which is alerting and reacting. So that goes to smoke detection, any type of fire detection system, We also have, basically, if we have an e-stop system or automatic shutdown of the, or disconnecting from the grid of the power, disconnecting the machine or the testing rooms. So these are all pieces that are important for the safety approach. And number 3, we have suppression of fire. So if those flammable gases that we talk about ignite and we have a risk of fire or we have an explosion, then we're thinking, do we actually have fire suppression in place? Do we have explosion control mitigation in place to address this specific hazard? And lastly, but not last, which is very important, which is emergency response planning. So understanding what should we do if we saw any sign of lithium-ion battery hazards or consequences in terms of manual actions, in terms of fire department connections. So any facilities should actually have early engagement with the local fire department to explain the approach, the level of hazard we're dealing with, and have a mutual coordination on what should be done. And then evacuation process. So personnel of the facility and the lab should be able to understand what to do in case of emergencies. And now I will hand it over to my colleague Mark, where he's going to talk about the battery testing lab configuration.
Thank you, Jihan. So up on the screen is what we're showing is a slide, and the image is from Fraunhofer ISE. And it's basically a somewhat a typical, what they had, a typical battery testing lab. As you look around the area, you have the functional testing and safety, impact shock, large drop test, and mechanical testing. That is just a few of the tests. This is just kind of a standard. There are other significant tests out there that some labs perform, some don't. If you're looking at, as we talked earlier, about abuse testing. So am I doing large-scale abuse testing? Do I need more of a fortified bunker area? Am I doing electrical testing, meaning am I shorting, overcharging? Those type of events, which would result in a much more robust type of lab. So as you're looking here, they actually have in the blue, they're showing how occupants move around the space. And those are important. The way people move throughout this lab is important because the people are the ones that are going to be bringing in and out the batteries as they're being tested. They're going to be removing the old batteries as they're being disposed of. One other areas they don't designate in here, which is critical. 2 other areas that we'd like to bring your attention is your shipping and receiving area, when all these individual cells or all these large-scale batteries, depending upon the size and capacity that's being tested, where are you storing them and how are you storing them inside of your facility? Am I storing them in an open warehouse, racks, however am I storing them? And then after the battery testing is completed, what are you doing or what is the client going to be doing with the old discarded batteries? I could have a suspect battery, that before testing I realize that there may be an issue with this battery, so I don't test it and I set it aside. And you also have the batteries, once they've been through their testing, particularly in the abuse area where you are intentionally puncturing the battery or you're using a side impact to crush the battery or top crush, however you're going to damage that battery, you are intentionally trying to put it into thermal runaway to find its effects. Where do you store those? How do you move them around your facility? How do you then get them out of your facility to a recycler or disposal company? One other area in here that they really don't show is control rooms, where the people, then the occupants, would sit and observe all the testing that's going on inside of the facility. Next, we're going to be talking about the hazard identification and evaluation component when you're looking at how we're creating and how we're life safety and how we're building these labs. So first and foremost, as the screen says, the most important issue when we're in all of this that we do is the life safety of the occupants. We want to make sure that everybody that comes in the morning and does their jobs, we know that lithium-ion batteries, they can be dangerous to handle to test, particularly when we're intentionally putting them into thermal runaway. We want to make sure that everybody goes home safe. So that's first and foremost. The second item is how do we protect the structure itself? So for business continuity, if a company wants to build a lab, they want to make sure they use it over and over and over again. So the other aspect is building continuity. How do I make it so that my test can be successful, I don't have any damage to my structure, i.e., passive fire protections, rated walls, rated barriers, deflagration venting, ventilation, and the other life safety components or occupant safety components such as eye wash stations and things along those lines. Across the bottom is the 4 items that when we're trying to determine all of those factors is what we look at as a holistic approach to creating a lab that can A, safe for occupants, and B, have total business continuity. The systematic search for the hazards, so we're always trying to ensure that we're properly identifying hazards. Sometimes, as we'll talk in other slides, as battery chemistries change, as battery capacity changes, the lab's testing procedures may change. So they need to ensure that they can adapt with the, what they want to do in the future. Regulatory compliance, obviously codes and standards, then optimization of the flow and minimizing exposure to hazards. Like I said, when you look at how these batteries are moved throughout the space, how they're being stored, how they're being handled, making sure you have properly trained people to make sure all of those components are being completed. And then the final is the prevention and mitigation of incidents. We obviously want to make sure that, somehow if there's a regulatory compliance, if we are working in a space that potentially doesn't have a regulatory issue on it, because some of this technology obviously is new and there isn't, a lot of prescriptive codes. So if there's something either A, that's prescriptive, but it may be lacking because a municipality may be using an older section of the IBC or the NFPA codes, whatever they're using, it may be older, so we would have to then incorporate that in to mitigate the hazards. This is just a flow chart, the hazard identification and evaluation process when we're working with these facilities and how we're going from, okay, we're going to build a lab all the way through the end. So first and foremost is hazard identification. We're looking at, okay, as Jihan talked about, we all know what the hazards are: thermal runaway, venting, explosion, deflagration, those type of items. Next is the risk assessment. Now with the lab, it's a little bit different and a little more complicated in some aspects, because when you're looking at the battery testing, what type of testing is the facility performing, and what exactly is the process in which it's going through. Like I said, if we have, a lot of times if you're doing a single cell, not so tragic, not so, hazardous or, hazardous to the occupants in the building. However, when I'm doing full-scale EV-type batteries and I'm putting them through abuse testing, the nail puncture is a good one, as you saw the video of just one cell being punctured by a nail. You have crush testing, there's shake and vibration and electrical testing. So the battery testing process would be looked at. And as we discussed, the handling and storage of when you're bringing those batteries into your facility, how are you properly storing them as they're waiting to be tested? How are you handling them as they're going from the storage to the testing chamber itself? And finally, what do you do with them once the battery tests are completed? You want to de-energize them, put them in a saltwater bath, you want to store them on a pad, in case you have reignition. Those kind of things is something that needs to be looked at, and client to client is different on their approach, but those are all the items that need to be addressed in that phase. Then the performance-based design, once we have the hazards identified, the risks identified, and first of all, we would look to the prescriptive code. If there's no prescriptive code that requires, then we would look to a performance-based design criteria for our fire protection, for our sprinklers, our fire alarm, gas, any sort of gas detection, any sort of ventilation rates that may be required, going into the deflagration and venting. We can do that by vents, we can do that by ventilation. There's several different, means and methods to do that. Then we have some consequence modeling, which we'll talk about in a slide or two, so I don't want to get too far into that. And then finally, occupant egress. That drops down to our cost-effective design approach. Now we know we have our hazards, and all of those hazards are properly identified. So we want to hit what we call the Goldilocks zone when it comes to your fire protection strategy. Obviously, we don't want it to be too little. We don't want it to be too much. We want it to be just right so that you're maximizing what you're doing, but you're not over-designing systems or under-designing systems. And that approach also allows clients to be future ready for adaptation to changes. You have other hazards identified. Sometimes it's easier to tweak them once they're already been identified, and also allows, as I said earlier, companies to change when it comes to changes in chemistries, changes in size, capacities, either A, as technology moves forward, and it's just you have that natural evolution of how the industry is going, or B, the other aspect is they just want to start testing more batteries, bigger batteries, different size batteries. And then the testing methods. If methods change, equipment is constantly changing, you have different testing equipment. And then last, I'll just touch on it too. We've mentioned it several times, but it is critical, the emergency response plan. And my recommendation on that would just make sure that if the lab is nearby, that they're talking to their local fire department and AHJs. They're the ones that are going to be responding. The next slide, I'll turn back over to Jens, my colleague.
All right, I'll insert myself back into the presentation to clarify the risk evaluation process. So Mark touched on that, Jihan touched on that. What we often find is when we work with architects, engineers, operators, yeah, we understand we have to do the risk evaluation, but how do we do it? And there are different methods available. So I'm briefly going to highlight or summarize the most popular ones. And then I pick on one that I typically recommend, that is the bow tie method, because we find that this is a very effective communication tool with all the stakeholders that are involved. And I wanted to underline, we are doing this because we had a series of lithium-ion battery-related fire incidences in the industry, and that's why we developed those type of tools, as a safety community. Problems typically go up with scale, right? So the industry has done a very good job mass manufacturing batteries, but if you put a lot of batteries in the same space, the probability just goes up that you have potentially a cell that is defective, right? So if you're looking at an operation like a testing lab or a manufacturing facility or like an energy storage system in ESS, indoor, large scale, we have to plan on a cell failure scenario. It's not really like an if situation, it's a when situation, okay? Here we go. So here's a common techniques that you typically see, and you also see this if you, for example, take a look at NFPA 855, the guideline for the installation of energy storage systems. That code also applies to the storage of lithium-ion batteries, has a great appendix with a lot of information, and it will highlight some of those methods. But so you will see like the FMEA, HAZOP, FTA, or bow tie analysis. They all have the goal to enhance safety. We want to optimize the process design. So there's really a feedback loop, right? So when we find something that is bad in the risk assessment, we can go back and address it, okay? So it doesn't need to end there. And we're going to try to reduce cost. We're going to try to do this in the design process, but also if all safety systems work well and you never have a catastrophic failure, that's really cost saving versus having a catastrophic event, right? And then also it is required for regulatory compliance. Typically when you have more than 600 kilowatt hours under a roof, you have to have a risk assessment in place. And that used to be a decent number a few years ago, but 600 kilowatt hours today is not really that much anymore. So the FMEA identifies failure modes, their causes, and the effects on the battery performance. We primarily see this when we evaluate a product. But what we want to do here is we want to evaluate a building or process in a lab. So what we could use there is a HAZOP, because we have processes like a HAZOP and a hazard and operability study, where we would systematically evaluate where do the occupants go, where does the battery go in the building, and we try to feed those feedbacks back in. Likewise, the power industry likes using the fault tree analysis. We see this a lot in the nuclear industry. There's a quantitative risk model. The other two as well, by the way. And you will build your fault trees and you make your little model and you go through that. I wanted to pick on the bow tie analysis, even though it is only, so to speak, a qualitative risk analysis tool. It's very simple to use and it's very simple to understand. Because we heard today that you need to engage with your authorities having jurisdiction, you need to engage with your fire departments, and they very often do not have the resources to review a quantitative risk evaluation, right? So, so it's important to have an effective communication tool. That's why we picked the bow tie, which is a common industry accepted risk hazard tool, and it provides a clear graphical presentation. And it actually does look like a bow tie. So that's a very clear graphical representation. Looks a little bit goofy. So if you do this as a professional, you have a software that you use, and then you can connect all the bow ties with each other, okay? And you make a very good model, and you can also document this in a narrative format. So it's very easy to review for an AHJ to review, or like for your CEO to review, right? So, but what you do, the event you worry about, your hazard event, you write that down in the center, and you collect all your threats and consequences on the left and on the right, respectively. And in this example, we were analyzing a test room fire, right, while we are abuse testing a battery. And so we thought, okay, what can happen here? You know, the threat could be battery overcharging, or an electrical fault, or battery short circuit. And then you write down what preventative barriers do we have in place. And in this case, we had a temperature alarm in place, we had voltage regulation in place, and we had overcurrent protection. If we would find that we have no prevention barrier for short circuit, now this would tell us, oh, go back and implement overcurrent protection. And then likewise, if those threats succeed and our preventative barriers fail, now we have a thermal runaway event. Now we're looking at recovery barriers, right? So if the thing is on fire, if like flammable gases come out and ignite, then we identified we have fire suppression in place for like an electrical fault. We have like reactive power compensation in place. If that fails, we would have an arc flash. And so we can inform our building design, we can optimize our process design, and we can inform our emergency response plans that way. And this is how this works in a nutshell. And then I hand it back to Mark to talk about the consequence model, which is needed when we really want to know how big is the event going to be.
Yeah, thanks, Jens. So on the screen, as you can see, we typically use a program. One of our main tools is what we call CFD, which is computational fluid dynamics. And let me read this, make sure I get it proper. It's a computer-based program that analyzes fluid properties to include temperature, pressure, velocity, and density. So as you can see on the screen is, for example, we created this CFD model for one of our clients because during their abuse testing, where they were physically going to do nail puncture and crush testing inside of that facility, the prescriptive code told them they needed so many square feet of venting to have this room. Well, they couldn't accommodate that amount of venting. So what we ended up doing is creating this model with the amount of venting that they could provide, and then that showed what would happen inside of that space. You know, how would the space, this also how it can affect the structure and how it affects walls and things along that line. And as you can see, you know, it simulates the panels blowing out. And so we've used this very successfully on, for example, large test bunkers, concrete bunkers that potentially don't do any sort of very minimal deflagration venting because they're concrete bunkers where they're testing very large-scale batteries. This is being used to determine that pressure and how that pressure then would react and push back on the structure. This video right here, we're just going to show you a video. It's venting in an enclosed space. Now this is provided to us by the University of Texas, just to give them their fire and research group. So that's where it came from. It's a 94 amp hour NMC battery or cell. It's just to demonstrate how a single cell at a 94 amp hour single cell inside of a 4x4x8 closet could react if it goes defective or something happens. Somebody is working in the closet and bumps it or does something to it. But as you can see, the exterior view, the internal view, and the back wall view are what basically happened, how much venting you had. You had the venting, then you had the torch, and then you had finally the flammable gases being ignited and the door coming off. So I'm going to turn it back over to my colleague Jihan to walk through some public domain case studies.
Thank you, Mark. So let's take a look at some public domain case study that highlights why hazard and risk analysis are important, why consequence modeling are also important to address any types of lithium-ion battery hazards. So this example here was in a battery testing facilities in 2022. This was an abuse testing of an EV batteries, and the images speak for themselves. Even we expect an abuse testing to actually result in the consequences of thermal runaway, but you can see here the exterior wall damage, there was excessive damage to the building, and this highlights why if we have a consequence modeling in place, an appropriate mitigation measure, we could potentially mitigate such hazards. There is another example here, also in a testing laboratory. This was in 2024 recently, and this was a stress test of an EV battery. And there was a response of 3 fire departments. The image show how there was excessive smoke coming out of the building, and the response here was actually taking that battery, putting it in a diving tank. Some of the lesson learned from this is there was no emergency response plan. So the 3 fire department arrived on site, and there was no coordination trying to understand what should we do with the battery in this case. So there was damage to the facility. So windows, you can see cables, and part of the building was partially damaged. Thankfully, no injuries. And this just highlights why having some of these important aspects in place could actually help with this type of consequences. And the last case study, this is not a battery testing lab, but it's a manufacturing plant in 2023. So the battery was in a storage area, in a shipping dock area, and Mark was talking how we can see this in testing labs as well. And it was hit by a forklift that causes the battery to go into thermal runaway. So if you recall, we talk about structural damage. That's one possibility. It's not always the electrical causes. So this was a 3 alarm fire response. There was 60 firefighters in place. There was no injuries, but the whole factory was evacuated, and there was extensive smoke that filled the entire building. And this was not the only incident in this plant. Specifically, there was like multiple incidents. So we want to just highlight all of the aspect that we talk about here that could play a role in addressing some of these consequences. And I will hand it back over to Jens to just summarize some of the key takeaway of what we just discussed today.
All right, thank you, Jihan. Well, we made it. This is the last slide. This is the key takeaways. So I hope you enjoyed what we highlighted here. We talked about a lot of different stuff. We talked about the hazards, that you need to perform a risk evaluation, that you need to potentially modify your process design, your testing layouts, and so on. It was a lot to swallow. So, but like, as key takeaways here is we want to highlight you got to comply with standards and regulations, right? So now where you can. So we know like for some of the testing operations that we have out there, there's not necessarily a standard on how you have to design your building, as like the whole industry is still catching up and the development of codes and standards is lagging behind, right? So, but like you need to meet the letter of the law, what we call standards and regulations, and as best as you can, and where it's not feasible, you need to make sure that you can meet the intent of them. One way to do that is by using the performance-based design methods like Mark was pointing out, right? So sometimes if there is a code, it can be very overly prescriptive on how I have to protect the building. And then, I can argue that I might be able to do a little bit less, so to speak. And if I have computer simulations done by knowledgeable people that can underline that it's safe. And then, the risk evaluation. Nowadays, that is something that you always have to do. Back a few years ago, that was something maybe you would have to do it. Nowadays, as batteries are getting bigger, you are just like reaching that 600 kilowatt hour threshold in no time, in particular in the commercial operation, right? So you have to perform that to develop effective fire and building safety systems. So having said that, we have about 5 minutes for questions. If you have questions, I can either like walk the mic to you, or you can walk up to the mic that is standing, as there's a stationary mic up front here. If you like a copy of the slides, please scan the QR code. It's on the screen, and it was on some of the chairs. We would be happy to share that. Likewise, this presentation was recorded, and we will be able to share that in a month or two. All right, I think the presentation was way too good. That there are no questions. Maybe to get it started, maybe I'll ask a question to Jihan, okay? Because you talked about the flammable gases and fire suppression. So I understand that fire suppression, that makes sense in indoor applications when we have a building, right? But I sometimes hear people talk about a let it burn strategy. And I think that comes more like from the energy storage industry. But can you shed some light on that?
Yeah, definitely. Thank you, Jens, for putting the light on me again. So yeah, so basically either if you're dealing with battery energy storage system fire or EV fire, sometimes the let it burn strategy is the way to go because if it's outdoor application, not near exposure, so we don't have building around or a risk of fire that propagates to any adjacent buildings. So the let it burn strategy is just let the whole thing burn. And we see many fire departments are going with these strategies. And one of the reasons for that is lithium-ion battery fires require large amount of waters. And just imagine you're extinguishing that fire. So all the water runoff has a lot of chemical components and toxic components. And dealing with the water runoff is also an issue that many facilities will have to actually address. So water runoff risk is one of the main causes for why sometimes let it burn is the way to go. And also another important aspect is the stranded energy. So once the lithium-ion battery fail, and even if you try to contain that failure, there would be a lot of energy inside that if it's not consumed fully, then you might have reignition risks. So that's why when a lithium-ion battery is damaged, we talk about how do we transport damaged battery? What should we do with? So there are various strategies like Dunkin' tank. There are various, I saw a couple of solution here of using some type of silica to put the battery in and kind of just like cover it, put in specific containers for shipping. So if the battery didn't consume itself, there is a very significant risk of having another thermal runaway event initiated. So these are some of the causes, and I was saying like if it's out there, remote area, maybe the way to go is let it burn, but you should also think about the plume of the smoke that would keep generating. How would we deal with that? Do we need evacuation zones? So these are all different aspects, and I would say they are site-specific. They vary based on the design, sometimes based on the HJ approach. That's why coordinating with the local fire department is very important to understand what's their preferred approach of dealing with battery. Are they knowledgeable enough? Do they have enough education? And this is part of what we do. We want to make sure everyone is educated about lithium-ion battery hazard. We share knowledge about what are the risks and what is out there in terms of suppressions. Yeah.
Very good answer. Thank you. All right, I come down there. Got a question from Mr. Scott.
Yeah, thanks, Jens. So you guys talked about a threshold of 600 kilowatt hours, I think it was, that triggers the requirement for hazardous risk analysis. What's the code? Is that an NFPA code? What's the code that requires that?
Yeah, that's out of 855, NFPA 855. And over the new versions between 855 and the new versions of the International Fire Code, before when you look at the older versions, the new 2024, and some of the codes, whereas 10 years ago when this was a fledgling industry, that was kind of all over. That one specific is right out of 855, and now they're starting to more or less coalesce between 855, between the IFC. So you're probably going to start seeing that a lot more in other codes or just referencing 855.
Yeah, and you will also see it in the IBC.
Yeah.
Yeah. And it's really something, that number traditionally came from energy storage systems. For lithium-ion battery mass manufacturing, it's a very small number, like a battery testing labs. Yeah. All right, I think we have room for one more question. Yes, go ahead, please.
So water's not a great suppressant. Have you seen any advancements being made in terms of a fire extinguisher for this cause? Because we have different types of fire extinguishers. Is anyone working on something that can actually deal with these battery fires, or there's just too much energy in there to stop it?
Well, to Jihan's point earlier, I think we got to look at hey, what's the location? If we are doing testing outside, and we're doing an abuse test or an electrical abuse test, and now hey, the pack runs away. It's a fine option to just let it burn, right? But if that happens inside one of those rooms that Mark showed, it's maybe we want to deal with that situation, right? And what's important, we need to differentiate here between lithium ion and lithium primary batteries, because for lithium ion, you actually would put water on it. There's no lithium metal in lithium ion, so that is at the moment the most effective way. But in a way, when you're dealing with a thermal runaway, it's an exothermic chemical reaction. So all what you're really doing with the water is you're just controlling the event and cooling the nearby area. You still sort of allow the event to conclude.
Yeah, and then real quick, so some of the other agents that are out there, maybe some gaseous type agents or things along those, along that path, they can put out the combustion process, so we no longer have, the torch effect, being released from a venting battery. However, there still is, as Jens and Jihan both said, that once that thermal runaway starts, it's just no stopping it. So that keeps going, and you still have gases being vented. So now, instead of having a combustion problem, I have a flammable gases problem, and I'm going to have a heat problem. And then when I interject oxygen again, now I have a big problem. So that there's really no, lack of a better term, magic bullet that's going to, or magic agent that's going to come in that, and say, hey, we're going to stop it all, because the whole process would be to stop the thermal runaway.
Yeah, and just a good example for what Mark just said was the Surprise, Arizona battery incident. You might Google that. There's a lot of great information to just talk about clean agents and effect.
Yeah. Very good. All right, we want to be respectful of everybody's time and the time of the next groups that will present. Thank you very much for attending. We will be sticking around here for a while, so if you have some follow-up questions, feel free to come to us personally, or if you scan the QR code and you reach out, I will be getting an email and I will be in touch with you, and we'll look forward to engaging. Thank you very much.
Thank you.
Thank you.